chapter 3 is titled The Hubble Constant as Gravitational Redshift. I begin that chapter by laying out my argument for relative black holes, I guess you can call it. The idea of an event horizon, a boundary that doesn't require an observer is nonsense, really, because that's using the Schwarzschild metric, and it places the black hole in a universe all on its own, and it claims that it's got a radius of X, whatever. This is wrong. I mean, this is not real. In the real universe, there's additional mass, and gravitational potential is an observer-dependent phenomenon. So everything's relative in relativity. Every object, every star can be considered a black hole for some observer. So if you could place the observer at some distance from this star, the geometry will be such that it looks like it's a black hole. It's unobservable. I mean, this is a coordinate artifact based on your choice of coordinates, but honestly, this is all black holes. Now, the possibility of a black hole does exist. I'm not saying that they're all coordinate artifacts, and the closer you get to them, they just turn into stars. Now, although that would be really cool, and it's possible for some black holes for this to actually be true. In other words, we see some black hole on the other side of the universe, and we're like, that's a black hole. If we were to get into a spaceship and go to it, as we get closer to it, the redshift actually decreases, because now we're closer. The relative potential difference is not as severe as it was when we were over here. And so now this object is no longer a black hole. We say, oh, it's just a galaxy. And so that's the point I'm trying to get across at the beginning of chapter 3, is that this idea that potential is relative. And this is mainstream science backs me up on this. There's several published sources that talk about this. Kerr is the most recent, I think. Well, maybe not the most recent, but it was recently popular a few years ago. I think it was 2023. He published a paper talking about there's no such thing as a singularity or something. Or at least there's no evidence that it always is a singularity, because you can have a rotating black hole, the Kerr metric. I think there was some recent news about the Kerr metric, a new discovery. Anyways, it's still relevant today. This is ongoing research, and this is all complicated, and it's been 100 years, and it's still debated. But this is the way general relativity works. This is the direction we're moving towards. This is not backwards, okay? When you're listening to me, this is the future of general relativity. It's not current, and it's not the past. This is the future. And so this idea that black holes are relative, that's perfectly in line with general relativity, because this is how a black hole is decided by its gravitational potential. Did you hear that pileated woodpecker? Pileated? I don't know if it's pileated or pileated. I've only read that. I've never actually got a enunciation. My dad says pileated. I like to say pileated. It's just pileated. I don't even know what that word means. I should look that up. They're amazing woodpeckers, but they're a little annoying. I'm on the porch. It's a nice day. Gravitational potential is relative. So you can say that the sun's gravitational mass, there's one solar mass within the one solar radius, and the observer is whatever distance from it, and then you can decide what the gravitational redshift is. That's fine and dandy, that's a great way to start. But now if you place that observer outside the galaxy, what happens? Does the gravitational redshift stay the same? Absolutely not. Now the gravitational redshift is going to be more extreme because the observer is in some low gravitational potential and the sun is in the galaxy. So it's an entire galaxy. It's not, it's the same concept as an atom versus an atom inside of a star. And this concept continues across all scales. And the larger, more massive an object is, the more massive and the higher gravitational potential a chunk of mass has relative to empty space, the more likelihood that it will be observed as a black hole for some observer. You can always find an observer and place them at some distance. Some distance. And as long as you place them in a low gravitational potential area, it's going to be a uphill climb. And that's why it's important to ignore this concept called homogeneity, because that just removes relativity from relativity. See, general relativity is the greatest name of any theory of all time. Albert Einstein was super, super smart. Everybody knows this, but man, he really nailed it. He absolutely nailed it with the naming, the framing, the rules. Everything in general relativity is absolutely phenomenal because the tools are there. So long as you just don't ignore them. You gotta follow the basics. And if you get back to the basics, then we can march forward. So that's the essence of the first part of chapter 3. In the second part of chapter 3, I kind of show my methodology. The way that I view this is the way that I started 16 years ago. This is what I did 16 years ago. I thought, what if the Hubble redshift is gravitational redshift? And I didn't have some professor to slap me. I didn't have some colleague to say I was crazy. No one discouraged me from calculating how much mass is necessary. And so, if you work from the Hubble's law and just assume that it's gravitational redshift, and then you create a distribution based off of that, what you're doing is reconstructing your observation. You're reconstructing the object that you're looking at and what it's in and the mass that it's in the center of. And so for 1 megaparsec, Hubble's law is around 72 kilometers per second per megaparsec. So if you're looking at a star that's 1 megaparsec from Earth, it's going to appear that it's receding away from us at 72 kilometers per second. If you assume that's gravitational redshift, then for a volume having the radius of 1 megaparsec, the mass density is around 4 times 10 to the negative 23 kilograms per cubic meter. And that produces that 72 kilometers per second. And then you can do 2 megaparsecs, 3 megaparsecs, 4, and so on, and find the amount of mass needed to produce Hubble's law as gravitational redshift for all scales. When you do this, you get a profile of around 1 over r. It's actually 3 times k, which k is this coupling constant, 0.833 kilograms per meter squared. So it's not 1, it's 3k divided by 2r, which is actually the better way to do it, to find a total mass, it's 2 pi kr squared. So it's 2 times pi times 0.833 kilograms per meter squared times r squared. And that's Hubble's law. That's the distribution in our universe. And so when people claim that there's not enough mass to create Hubble's law as gravitational redshift, they're wrong, because all you have to do is just solve from Hubble's law. Just work backwards from it and find out how much mass you need. And it's not that much. It's exactly what we observe. It's the 1/r relationship. That pretty well sums up chapter 3. So the next chapter is actually the best chapter, I think. Chapter 4. And that's where I show you how we validate this thing using the cosmic microwave background radiation. So don't miss that chapter. At least read the next chapter. Then you'll really get it. Especially the commentary. I'm not sure the text will translate as well to all readers. So make sure you read next chapter and listen to the commentary. Let me also remind you that this book is not free. I want you to read this book, but I also want to make $5 off of it. At least something, like I'll probably raise the price in the future, but I'm going to leave it at that price for now. And that's not asking for much. I've put a lot of work into this. I've put years and years and years. Okay. And everything I'm doing, I'm doing it just like it's because it's an obsession. And so it would be really nice if I could make enough money to not have a job. So that's my goal, is to make enough money to not have a job. But that's not the goal of this book. Like, I don't really care about that. Like, the only thing that I want to do is spend time on promoting this idea. And the only reason that I want to do that is because I'm obligated. There's no way I'll ever get rich from this. This is not a way to get rich. I just need enough proceeds to be able to devote 100% of my time towards it. And so just buy the book. I mean, like, what is it? You subscribe to Netflix. You give your money to evil people all the time. You can give it to some dude that's trying his best to come up with a new cosmological model that makes sense. Like, I mean, I'm asking for $5 right now. Like, that's not much. And you're listening to the video. But, if you ain't got it, then you ain't got it. You just owe me. Okay? You owe me $5. If I ever see you, you have to buy me a beer or something. YouTubing sucks. Make sure you thumbs up, subscribe, leave a comment. Bye-bye.